Hi everyone, in this video we're going to talk about scatter plots and the correlation coefficient. I already posted a video that discusses more in depth what the correlation coefficient is giving us. So I'm going to go in this video straight to the examples that were from this notes. And so essentially when we look at a scatter plot, we're looking for the form, direction, and the strength of the relationship, the association between the two variables. And in this case we usually have two quantitative variables from the same sample. And so the correlation coefficient is what tells us how those variables are related. The closer to 1 or to -1 that they are just tells us the how closely they are represented by a line and how closely they are related, right? So if your correlation coefficient is positive, that means we are in the positive, there's a positive association. And if it's negative, then that tells us that there's a negative association, meaning as the dependent variable or the independent variable increases, a negative association means that dependent variable decreases. And a positive association means when one increases, the other one increases as well. And so these were just some examples of indicating a negative correlation, right? As the x variable, the independent variable, increases, the y variable, the dependent variable, is decreasing. In a positive linear correlation, they're both increasing. No correlation, so in here we should see the value of r be really close to 0. And this is a nonlinear correlation. So the first example we had is just house prices, and here it was just to identify the variables, the observational units, and trying to figure out how we can use that information to start setting up a correlation example. And so what were the observational units? Houses in Arroyo Grande. So the addresses, or the houses essentially. How many variables are reported in the table? There were two variables. We had the price and the size of the house. So both quantitative and both continuous, right? When we talked about quantitative variables back in chapter 1, we talked about continuous or discrete. Discrete are the ones, for example, like number of children that a family has, right? That's discrete because you can have 4, 8, 1, 2, but you can't have the values in between, right? You can't have like 4.333 children. So that would be an example of discrete versus continuous. Here, the size of the house, 1844 square feet, 1615 square feet. You can have anything in between. So that's continuous. And this is the scatter plot. And so I just gave this as an example with saying consider the following scatter plot of price versus size. And this tells you a lot when you see price versus size or something versus something, right? The convention is to say y versus x. So when you want to see a relationship of price versus size, that tells you, okay, so the price is the dependent variable. The price depends on the size. So size is the independent variable or response variable. Size is the explanatory variable. And so looking at this, we can talk about, okay, so the three things to look are form, direction, and strength. So it appears to be linear, right? You could easily fit a line here to represent this data. So it does appear to be a linear association. And then direction, it's positive, right? As the size of the house in square feet increases, so is the price. So for some, right, the scatter plot, those are all the individual values, and then we could do the line of best fit to represent this increase. As the size of the home is increasing, so is the price. And so we said the direction is positive association, as size increases, price increases. Strength is a strong association. We can definitely tell that as the size increases, so does the price. So we can say that is a strong association, and it appears to be linear. And so let's look at our next example. Televisions and life expectancy. So this table gives information about the number of TVs in a country, the average number of televisions per thousands of people, in 22 countries, and then the life expectancy. And so you can kind of see all the 22, is that what it was? 22 countries, their life expectancy, and then the TVs per thousand people. So again, these are quantitative variables. And so my question was, which of the countries listed has the fewest televisions per thousand and which has the most? And so the fewest was Haiti with just 5 TVs per thousand people. And then the most was the USA with 844 TVs per thousand people. So we can find this data in Statcrunch, and we want to produce a scatter plot of life expectancy versus televisions per thousand. So again, this tells you Y versus X. So that tells me that life expectancy is my Y and televisions per thousand is my X. So response variable is life expectancy, explanatory variable is televisions per thousand people. So let's go to Statcrunch and find that data. So once you open up Statcrunch, you want to go to My Statcrunch and you want to go to My Groups and find our group. And then we're looking for the data that was TV Life. Is that what it was called? Let's double check. I think that's what it is. Yes, TV Life. Oh, Life in Statcrunch. And these are instructions. So once we're there, we pull up the data. We're gonna click Stat. We're gonna look for regression from the drop-down menu, and then we're gonna select Simple Linear from the sub-menu. And then we're gonna just select the columns that we want for the X variable and for the Y variable. And notice we're gonna go back over here to say we want life expectancy versus televisions per thousand. So life expectancy is our Y and televisions per thousand is our X. And then we're gonna click compute, and we're gonna click the arrow at the bottom of the results to view the scatter plot. So the first window you'll see is a bunch of numbers, and we'll make sense of that in a little bit, but then we just want to look at the scatter plot. So let's go back, and TV Life, there it is. And here's the data. So I have 22 countries. Make sure that the data matches what you were told in terms of the number of values in it. So we're going to go to Stat, our menu Stat, and then find the regression. So there's regression, and then that submenu we're going to pick Simple Linear. So click on that, and this window will pop up with the variables that we want. So our X variable is the TVs per thousand, and our Y variable is the life expectancy. Remember, we're doing life expectancy versus TVs in the household. So life expectancy is our Y. And we don't need to put much of anything. We're not doing any hypotheses or confidence intervals yet. So let's just compute. And this gives you a bunch of numbers. And so let's just scroll over to the right, and there's the scatter plot. It already draws the line of best fit. But notice that this is our scatter plot. So we can copy it and then put it in. So we can just go copy image and then put it in our notes, and then we'll analyze it. So let's go back to our notes and paste that in there. So the question here is, does there seem to be an association between the two variables? If so, describe its direction, strength, and form. There is an association. It appears to be linear. You can say that it is linear. It's definitely not. So looking back at the examples of the different correlations, right? Like this means no correlation at all. And then nonlinear has a different kind of shape. And this is a very strong, like super strong linear correlations, but we definitely don't have this, right? We do have some correlations. So where is it? And we can say it's somewhat linear. So we'll just say it is linear. And then what about its direction? It's positive, right? As the TVs per thousand are increasing, so is the life expectancy. And it's pretty strong because it is clear to see that as the number of TVs in the household increase, the the life expectancy is increasing. So that's a strong association in terms of being positive. And so positive direction in association, strength, moderate to strong. That's what I had written, but we can say, I mean, it is, I guess here is the reason that I said moderate, because it's like, yeah, it's increasing, but here you can really see as the TVs increase, that is definitely increasing also. So that will mean a strong positive association. And because the associations are strong, one might conclude that simply sending television sets to the countries with lower life expectancies will cause their inhabitants to live longer. So comment on that argument. Why is that a faulty argument? And essentially, just because there is an association does not imply causation, right? There could be other things going on. So that is one of the big things here, that association does not imply causation. So the countries with lower TVs per thousand also have less access to technology. They are less developed countries. They have less access to nutritional food, perhaps, and to healthcare. So those are examples of confounding variables or lurking variables, variables that are not measured, that could be the true cause for the response variable, right? So having being a less developed country with less access to healthcare will definitely impact your life expectancy, right? If people have an illness and they don't have the healthcare to take care of, to get the proper care, it's going to decrease their life expectancy. So those are some of the lurking or confounding variables. If two variables are strongly associated, does it follow there must be cause and effect? No, right? Association does not mean causation. In this example is a great example. Just sending more TVs to Haiti is not going to make the life expectancy go up. What we would need to do is be able to provide better healthcare and nutrition or exercise, things that would improve quality of life to then improve life expectancy. And so here we already listed a bunch of the confounding variables, right? So in the case of life expectancy in television sets, suggest a confounding variable that could be associated. So we could say healthcare. And so now what about the correlation coefficient? A measure of the strength in the direction of a linear relationship between variables. If that's what the correlation coefficient is. The symbol R is what represents that relationship. And the formula for R is this lovely little thing. This is good for calculators. This can also be thought of as the sum of the product of the z-scores of x and the z-scores of y. It's divided by n-1, the degrees of freedom. The range of their correlation is from -1 to 1, with 0 being no correlation, 1 being a perfect positive correlation, and -1 being a perfect negative correlation, and like very linear. So let's try this next example. Calculate the correlation coefficient for the gross domestic product, so the GDP, and the CO2 emissions data. What can you conclude? And so here, essentially, we want to see, is there an association between gross domestic product and CO2 emissions? So what is GDP? So think about what that means, or you might want to pause the video and Google it if you're unsure. But the GDP is essentially measuring the economy of a country, right? So the in terms of exports and economic growth in that particular country. So this is, so the highest one there, 5.4 is the highest. So that would be like a very well-developed country. But then notice their CO2 emissions are also very high, right? So when you have, when you're able to export and have a high producing country, it comes at a risk. So what are you putting out into the air? Whether is you're exporting cars or anything with industrial means, then that's putting a lot of CO2 emissions and creating a carbon footprint that is higher than countries that are not as economically developed. And some background as to why I chose this example. This came about from a study I was reading about the impact of China's development on the environment. And so it just kind of made me think about like, oh, well, what are the countries that have the highest um, industrial development, and then how are they impacting the environment? And so that's kind of where this came from. It's like, okay, how does the economic development of a country impact their carbon footprint on the environment? So this is essentially asking like, does the GDP, your economic growth, impact the environment? And so we want to see that association. So we'll do this by hand before using technology. And so here I already kind of did some of the calculations. If you were going to do this by hand on your own, this is what you will do, right? So XY is you do X, so this is X times Y. So 1.7 times 620, that's how I got that. An easier way to do this is copy these two columns and just pop them into Excel, and then have Excel do the math for you in terms of multiplying X times Y, then squaring X for this column, and then squaring Y for that column. So that's where this came about. And then at the bottom is the sum of that entire column. So we have all our values here. When we look at the formula, where was the formula? Right here. So we need the product X times Y, and then we need to add them up. The sigma means add them all up. Then we need just X and add them all up, just Y, add them all up. And then we need the sum of X squares, right? So do X squared for each X and then add them all up. And so that's why in this table, we're finding all those values. So there's every piece that we need for the formula. And so once you put everything in, right, N is 10, we have 10 countries here. The sum of X times Y, that's this. So that's that number minus the sum of all the X's. So that's the 25.7 here, the sum of all the GDPs, the sum of all the CO2 emissions, sum of Y, and then on the bottom, the square root of, so there are two square roots here. So the square root of N, so 10 times the X squared minus the sum of all the X's, and then that square. So that's different. Right here, I'm squaring the X's first and then adding them all up. So that will be this one, squaring all the X's and then adding them all up. This one is take all the X's, add them all up, so 25.7, and then square that number. So that's what you see here, the 25.7, and then square. And then the same thing with the Y's. And the sum of the Y squares minus the sum of the Y's, and then square. And so we get R is 0.874. So that's a pretty high R, right? So that tells us, remember the range was, we said R goes from -1 to 1. 0.87 is pretty close to 1. If you were going to round it to one decimal place, it will be 0.9, which is really close to 1. So we will have a really strong positive linear correlation. So that's what we can say about that one. And once you've calculated R, the sample correlation coefficient, you want to determine whether there's enough evidence to decide that the population correlation coefficient, which is denoted by the Greek letter rho, is significant. So how significant is this correlation? So we're going to use table A6 from our textbook to interpret this R. So we're going to find the critical value and then determine if, so there is a correlation if the absolute value of R is greater than the critical value. Then we conclude that there's significant evidence. And if there's no correlation, the absolute value of R will be less than the critical value. And so let's do that for this, and we'll have then we'll go into the hypothesis test and find a test statistic. So here we're going to determine solely based on R and using a significance level of 0.05. So let me highlight that. What are, if we have sufficient evidence to support a claim that there's a linear correlation between GDP and CO2 emissions. So let's look at the table, which when you go to your textbook, it will be, you will go, if you go to the table of contents, you will go to Appendix A, tables. And so once you click on that, then you will find your table A6. We're at the 0.05 level of confidence for alpha, and our degrees of freedom are, what are our degrees of freedom? So let's go back. For degrees of freedom, we use n minus 2 degrees of freedom, and the minus 2 is to account for the variation in x, n, and y. So we get 1 degree of freedom for the x's and then 1 for the y's. And so that's how we will get our, so n minus 2. So because we have 22 here, our degrees of freedom will be 20. So we're going to go to 20 and 0.05 level of significance. So notice here critical values of the Pearson correlation coefficient are. So our degrees of freedom will be 20, right? 22 minus 2 is 20. And so our critical value is 0.444. So let's take that to our notes. So with 22, our sample size 22 minus 2, so with 20 degrees of freedom at the 0.05 level significance, our critical value is 0.444 from table A6. So let's go back to the condition. So it tells us that if the absolute value of R is greater than or equal to the critical value, we conclude that there's sufficient evidence to support the claim of a linear correlation. And if the absolute value is less than the critical value, then we don't have enough evidence. And so our R is 0.874, which is already positive, so the absolute value of a positive number stays positive. So that's our R. So let's take that and put it over here just to state our conclusion. So we're going to say R equals 0.874, which is then greater than our level of significance or critical value, sorry. So we conclude that there is sufficient evidence to support the claim of a linear correlation. And so this is determined solely based on R. So the other thing we can do to test the significance is do a hypothesis test for the population parameter rho, right? Rho is the population correlation coefficient. So for a hypothesis test, you will have the 3 different hypotheses. So you can have a left tail, which essentially just means that you're saying the rho is less than 0, so you have a negative correlation. You could have a right tail test saying that the correlation coefficient is greater than 0, so you have a positive correlation, or a two-tail test, just simply that there is a correlation. It doesn't matter which way, but that there is a significant correlation. So to do a two-tailed or a hypothesis test, we need a test statistic so that we can find a p-value. And so the way that we find the test statistic is a t-test statistic, and we find it by using the sample correlation coefficient, so R, divided by the square root of R1 minus our correlation coefficient square over n minus 2, which is our degrees of freedom. And so this is essentially the standard error, right? So you have your sample statistic. Normally it's the sample minus the parameter, but notice that in all the hypotheses, the parameter is 0. So we're always claiming for the null hypotheses that there's no correlation. So that will always be 0. So usually when we write a test statistic, we say the sample statistic minus the parameter divided by the standard deviation of the samples. So then this will be R minus rho, but rho is always 0. So that's why you don't see it in here. So we can find the test statistic for this. So let's do that real quick. And then we'll use a 0.05 level of significance. So we need to write the hypotheses and find a test statistic, and then either draw the critical region or find the p-value. So let's do all of that. So which hypotheses are we going to use? So let's look at the problem again. So we wanted to calculate the correlation coefficient for the gross domestic products and carbon dioxide emissions data. What can you conclude? So we're essentially just trying to see if there is a correlation. So we're going to use a two-tail test. So oftentimes when it's not specific, you want to be able to see I guess it's here, claim that there is a linear correlation between the gross domestic product. So that is a two-tailed test. If it said the claim that there is a positive linear correlation, then it will be a right tail. If it said the claim that there is a negative linear correlation, then it will be a left tail. Most often than not, it's just you're going to try to see if there is a correlation, regardless of which direction. And so most of the time, it will be a two-tailed test for these guys, for correlation. All right, so then we have our hypotheses is there's no correlation between GDP and CO2 emissions, so rho equals 0. And then there is a correlation between GDP and CO2 emissions. And finding the t statistics, so we look at this, r over 1 minus r squared over n minus 2 degrees of freedom, which actually I just realized as I was calculating this that our degrees of freedom, I stated them wrong here. Our n is 10. I was thinking of the TV Life problem where we had 22 countries, but here we only had 10 countries, so that will be 8 degrees of freedom. So does this change? Let me go back and look. So when I look at our table, we're still looking at the 0.05 level of significance, but now our degrees of freedom are 8, so 0.707 is actually our critical value. And so 0.707, but our r is still larger than that, so 0.707. Sorry about that. I was still thinking the 22 from the other example, probably because I was going too fast from example to example. So 0.707 is our critical value from table A6. So just to correct, I did not have my n correctly, right? The n in this problem is 10. I had it here. Why did I think 22? In the other example, the countries and the numbers of TVs, that was 22. So that's where my error came from. So I could have edited the video, but I kind of wanted to, not to create confusion, but I wanted to show you how it is still to make little mistakes like that. When you go from one problem to the next, you might still be thinking about the previous problem. And so I just wanted to, I could have edited the video. If you would rather, just for in future, me edit the video, let me know instead of showing the error and going back and fixing it, because I don't want to create confusion. But let me know if you would rather me edit the video out of and not include errors like that. All right, so now that we have the proper degrees of freedom, sample size is 10, so 10 minus 2 is 8, right? So not 22. Our critical value is still okay. 0.707 is smaller than our r, so our conclusion luckily is still the same. We conclude that there's sufficient evidence to support the claim of a linear correlation because our r is greater than the critical value, right? The absolute value of r. But because our correlation coefficient was already positive, stays positive. Now our test statistic here is 5.087. So we can either draw the critical region or find the p-value. So if we're going to draw the critical region, we want to look at our t values, right? The critical values to be able to draw the critical region. So we had our level of significance as 0.05 and our degrees of freedom are 8, 10 minus 2. So let's look at our T table. So right now I'm on Appendix A, which is my table A6, and I've kind of written down the page number. So table A6 is on page 692 of your ebook. Our T table is on page 686. So I'm just going to go over here to the book and type in 686, hit enter, and it's going to take me to my T table. And so it is a two-tailed test, so 0.05. And our degrees of freedom are 8. So I'm going to go to degrees of freedom 8 and 0.05. So 2.36. So that is my critical value for using the t-table and to be able to find then the p-value. So 2.306. So let's take that over here and let's draw the region. So we will draw our t-distribution, which kind of looks like a bell curve, right? And so then we're going to have, based on the table, we know that with alpha equals 0.05, then, and it was a two-tail test, then I'm going to have alpha over 2 at each tail. So this is alpha over 2 will be 0.025 on each side. And this is 2.306 if I remember correctly, and then minus 2.306. So that is our critical region, right, which is also, I like to call it the rejection region. So when you have a two-tail test, you have two, so rejection region. And notice that the 5.087 will fall in the rejection region. So 5.087 is over here. So we will say we reject H null. And the null hypothesis is that there is no significant correlation. So we reject that claim in favor of the alternative, saying then there is a significant correlation between GDP and CO2 emissions. And to find the p-value, we will have to use either StatDisk or Statcrunch to do it. So let's use Statcrunch. So to be able to use Statcrunch, I will go to my table and just copy those. Actually, we'll copy the whole with the titles and then go to Statcrunch and paste them right at the top. You just select the first one and hit paste. It will populate the whole thing. And so now I have my data here. We're going to go to Stat and Regression, and we're going to go to Simple Linear, and we're going to select our X, which is the GDP, and our Y, which is our CO2 emissions. And now we are doing a hypothesis test, and so we want to make sure that this matches our hypothesis. So this is always going to be 0, but here the alternative, we want to make sure that we choose the correct one. We are doing a two-tail test, so we can leave it as not equals, and we can now hit compute. And now all these numbers are gonna make sense. So notice that in Statcrunch we get our R, correlation coefficient, 0.874, which is what we got doing it when we did it by hand. So that's our R, so that's good. And then our T statistic. Now what was our T statistic? We got it to be, where was it? 5.087. So let's go back to Statcrunch and notice that the one is actually, we're looking at the one that says slope. And so our T-stat is 5.099. So we're pretty close, right? If we rounded it, it will be, if we rounded ours, 0.087, it will be 0.09. So this one is close. Statcrunch, of course, is using more, it's not estimating as much as we were. So our p-value, 0.009. So that's then what we look for. Our t-table unfortunately doesn't give us p-values, right? It's just giving us the critical values for the critical regions. When you have, in this case, a two-tail, just give us the critical t-value for each, the positive and the negative, but I don't get p-values here. So we have to rely on either StatDisk or Statcrunch to do it. So our p-value is 0.0009. So we already did it by looking at the rejection region, critical region, and we see that we reject the null. Now when we look at the p-value, remember gives us the area beyond 5.087. So the area below this t statistic is going to be smaller than our alpha. So it lays within there, so then we reject the null hypothesis as well. Therefore, since our p-value of 0.009 is less than our alpha 0.05, we reject the null hypothesis in favor of the claim that there is sufficient evidence to I guess I redundant here, support the claim of a linear correlation. So there's sufficient evidence to, which one should I get rid of? I'm just going to say instead of the claim here in favor of the alternative. So we reject null hypothesis in favor of the alternative, that there is sufficient evidence to support the claim of a linear correlation. That's what the alternative hypothesis says. All right, so then that's how you do this in Statcrunch. So the only other thing is causation, right? Does correlation imply causation? We already said no. Sometimes, like in this case, we can probably say that if the variables, if there's no other co-founding variables, then you can probably say that correlation implies causation. And in this case, right, what other could you find co-founding variables that are causing CO2 emissions? And it might be hard to say that there are other things that are not the things that are contributing to the economic growth of a country that are causing CO2 emissions. In this case, if you can't find other co-founding variables, it is likely then that this correlation will imply causation. So essentially, you can only deduct that there is causation if there's a lack of co-founding variables, right? If there are no other way to explain the relationship, then it must be, then that correlation can imply causation. But you have to really make sure that there are no other co-founding variables. And let's see. And so you could also think about a reverse relationship. So the first thing is there a direct cause and effect relationship between the variables? Does X cause Y? So does the increase in GDP cause CO2 emissions? Or is there a reverse cause and effect, right? Does Y cause X? Does CO2 emission cause GDP? This one will not be likely, but in a different example, there might be a reverse relationship. Is it possible the relations between the variables can be caused by a third variable or a combination of several other variables? So those are the co-founding variables. So if you, like I said, if you have a hard time finding co-founding variables, then likely that the relationship between the original two variables may be causation. Okay, so let me end there, and then I'll record another video for the next two sections, 10.2 and 10.3. Email me if you have any questions.